Hello and welcome to the first online lecture of BME306 that we're going to be discussing cross-correlation. So you might be familiar with the concept of correlation. Most likely it's a statistical correlation. This is basically the relationship between two different variables. So correlation is a relationship between two different variables. So suppose we have some height and weight data. In this case it's just from the Chicago Blackhawks hockey team. And if we want to determine if there's a relationship between height and weight, often we'll plot the variables against each other. So we can plot the height data point against the weight data point. If you plot the remaining points in the table, you'll see that there is in fact a relationship between height and weight. So people that are taller tend to weigh more. What you might want to do is you might want to put a line of best fit or a linear model into this data to a little better characterize the relationship. So you might use a regression to put a best fit line in here, and then the statistical correlations may be captured by the slope and the offset. It's a very reasonable thing to do. It's used all the time in engineering problems. It's just not what we're going to be talking about today. We're going to learn more about regression and model fitting in BME307. And I only bring this up so that you're not confused if maybe you've heard of correlation before and you think of statistical correlation. We're going to be working with cross-correlation. So cross-correlation is a little bit different. So suppose you have two signals, x of t and y of t. The cross-correlation between these signals is defined by the integral. So the cross-correlation between x and y is a function of tau, and we'll get into tau in just a minute. If you integrate over all of time and you multiply this x of t times the y conjugate of t minus tau dt, that's the definition of the cross-correlation. We'll try to get an intuitive feeling for what the cross-correlation is as we go through a few examples, but for right now this is a definition. This is also an equivalent definition if you do some variable substitution. So either of these two definitions will work. We'll be focusing in our examples using the first definition. A couple notes. First off, one of the signals is time shifted. So remember in our review, if you have a t minus variable as your argument, the resulting property is to shift the function left or right in time. Second off is we have this tau variable. So tau is a time-like variable. It's often referred to as a delay or a lag or a shift. It's a little bit. This is a little bit confusing to some people, and we'll wait until we get into some examples. And if you have still questions, maybe we can cover it in class. But tau is it's often referred to as a delay, a lag, or a shift. And the final thing to note is that y of tau or y of t minus tau, the star means that it's a complex conjugate. So we're going to be dealing mostly with real signals. So when you see this conjugate notation, we won't worry about it for at least the first few lectures, and probably not until actually we get into Fourier transforms. So we're going to deal with real signals. So y conjugate of tau is equal to y of tau, or y conjugate of t minus tau is equal to y conjugate, or is equal to y of t minus tau. So we won't worry about the complex conjugate in our first few examples. Okay, so we're going to do a couple of examples where we work out the cross-correlation. Eventually we'll do examples where we actually use this definition of the integral to work out the value of the cross-correlation. But to start with, we're going to do it graphically using pictures. So kind of pictorial cross-correlation to see if you can get some sort of intuition or feeling for what this cross-correlation function is all about. So we're going to start off with two functions, two signals, x of t and y of t. We'll make it so that both of these signals are real, so that the complex conjugate of y of t is equal to y of t itself. So it's a real signal. They're going to be rectangular shaped. We often use these for examples. They're convenient to work with. And we'll say that they're the same to start with. They both have widths of 4 and amplitudes of 1. So if we're going to work out the cross-correlation, first thing we need to do is we take our x of t, we draw it. as it exists, as it's defined. And then we look at the y of t. So it's y conjugate of t, actually. I'm just going to call it y of t because it's a real signal. And we look at this time shifting property. So at very negative values of tau, or of delay, we're going to see that y of t is shifted. So if it's, say, for example, minus 10, so y of t minus a minus 10 is equal to plus 10. So y of t minus 10, say shift left of 10 units. The thing we note here is that these functions do not overlap in time. So x of t times y of t plus 10, you multiply them together, there's 0 everywhere. So the multiplication of x of t has 0 values out here. Anything times 0 is a 0. So the value of the cross correlation at these locations are 0. Similarly, for large positive values of tau, the value of the integral is 0. The functions do not overlap, so the value of the integral is 0. So what happens when they get close to overlapping? So we know that tau is equal to minus 4. We have the functions defined. They overlap because there's 2 units, plus 2, minus 4, plus 2. They start to overlap when this function is centered at minus 4. And what's going to happen? So as the functions overlap, the area that's intersected by the functions grow. So basically, this here is now no longer non-zero. So it's actually equal to 1. And if you integrate, take the antiderivative of a constant, you get an x, kind of a straight line. We'll go more into detail and work some out with specific functions later. But just in this simple example, this is going to be a constant value. It's a 1. The integral of 1 is x. Could be modified a little bit, but it is kind of a linear function. So it grows until they're completely overlapped and it reaches a peak. This area, when there's completely overlapped, is equal to the width of 4, the amplitude is 1. So the area of a rectangle of width 4 and amplitude 1 is 4. And then as you continue to shift the function along, the area that's intersected by these two functions begins to decrease linearly up until positive 4, at which point they no longer intersect anymore. So this is the cross correlation worked out for 2 rectangles. And just so you know, sometimes the cross correlation of the signal with itself, so x of t equals y of t, or x of t and x of t, that's sometimes called the autocorrelation. It's denoted by rxx of tau instead of rxy of tau. Just convention is another definition. So that's how you work out graphically the cross correlation. We're going to do a couple more examples to get a feel for what this means in a little more detail. So let's do another example. In this case, we'll say x of t is no longer centered at 0, it's centered at positive 2. So the rectangle has been shifted over 2 units. So if we want to work out the, again, if we want to work out the cross correlation, we replicate our x of t, and then similar to before, any places out here that are really negative and any places out here that are really positive, the functions aren't going to interact, or aren't going to intersect, and the value of the integral is going to be 0. At the points where they do intersect, and you see that again, whereas in the previous example it was at minus 4 they started to overlap, in this case they begin to overlap at minus 2. So at minus 2 the functions begin to overlap. When tau equals minus 2, the functions begin to overlap. When we get to positive 2, the functions are completely overlapped. They're both centered at 2. We again get our area of 4. Continue to slide on y of t. The value of the cross correlation begins to decrease, again linearly, out to the point where it's centered at 6. At this point, centered at 6, the value is now 0 again for all delays more positive. So, a couple of things that you should start to recognize are that the peak of this cross correlation, it's related to the point at which the functions overlap or where they're centered. So if you're looking at this function x of t and you are doing the cross correlation with y of t, you'll notice that it's centered at a shift or a delay of 2. So what we're beginning to see is that the peak of this cross correlation kind of it's looking like it may be related to how this function is shifted in time. So that's the first point. We'll get on to some other properties of or meanings of cross correlation as we do again another example. Alright, so let's do an example that's a little bit more difficult. So in this case, we're going to be doing the cross correlation of a shifted rectangle with a triangle. Again, just to get a little bit more of a feel for what the cross correlation is. So again, we replicate our x of t. We should be now have convinced ourselves that any place that the functions don't overlap, that the value of cross correlation is going to be 0. So in this case, anywhere is up to 0 on the tau axis, these functions are not going to overlap, and the result is going to be 0. Similarly, anything greater than 8 on the tau axis, there's no intersection between these functions, and the value of the cross correlation is going to be 0 at all of these locations. We probably can figure out what's going to happen when the functions exactly overlap just from the values I've chosen, since they both have widths of 4. So we know at tau equals 4, this is just going to be the intersecting area from them, so that's going to be 1/2 the base of the height times the height of the triangle. If the base is 4 units and the height is 1, that's going to give us the value of the cross correlation of 2. What we're interested in is figuring out how it gets to this value and how it decays back to 0. So in order to figure that out, we actually have to work out the integral, the cross correlation integral. So if we look at the cross correlation, anywhere is up to and including 0, the integral is the value is going to be 0. So the lower bound of our integration is 0. The upper bound of the integration is going up until the shifted value tau. So the lower bound is 0, because anything below 0 is when you multiply them, it will be 0. The upper value is tau. This is the equation of our line. So y equals mx plus b. The slope is -1/4. The intercept is 1. This is the equation of our line. This is our shifted y of t. It's equal to 1. So unity value of 1. So when we do this integral out and simplify, we get a cross correlation in this region of tau minus tau squared over 8. And you should double check that because I just did it really quickly a few minutes ago. But a little sanity check is if we plug in 0 here, we know that it should start from 0, and we get a 0 minus 0, so the value is 0. And if we plug in at 4, we should get the value of 2. So if we plug in 4 minus 16 over 8 is 2, so 4 minus 2 is 2. So that's a good sanity check. So this is probably correct. Similarly, we want to figure out what is going to happen in this region, and we're going to have to work out the integral again. So what we need to note is that the upper end of the integral is 4. So anything greater than 4 it's multiplied by 0. There's no values here. The lower end of the integral is the tau minus 4 units. So that's the lower end of the integral. So it's tau minus 4. We do out that integral again and simplify it. We get tau squared minus 2 tau plus 8. Once again, I'd suggest that you double check that value. So in this example, we've worked out the cross correlation of a rectangle with a triangle. So again, these are just artificial functions, but we're getting a little bit more complex. We're going to do one more example, and then that'll finish up this. We'll summarize some of the points we've learned, and that'll finish up this lecture. So we're going to do one final example. In this case, we have our YT. It's non-zero at two different portions of the signal. So we have kind of a triangle function out here at time equals 4. We also have a triangle, which is the mirror image of it at time equals -4. We're going to do the cross correlation with signal x of t, which is identical to the triangle on the right. So again, we should know that we have non-zero values for the cross correlation up until the signals overlap. So where this first triangle starts to shift across, we'll start to get non-zero values. And I'm not going to work out the values exactly, the equation of the curve, as I did in the last example, but you could do it very easily by using the definition of the integral. So it's going to have some curve. It's going to be quadratic shaped, and you can confirm that for yourself. It's going to reach a maximum when the signals are completely overlapped, and then it's going to start to decay. And it goes back to 0 for quite a while until we get the second portion of the signal that is non-zero that's going to be cross-correlated with x of t. So when this triangle reaches the x of t, again we get a non-zero value of the cross-correlation, and then when it shifts completely across, it's going to go back to 0 for the duration of the delay or the lag. So I haven't drawn these curves exactly, but they are representative of what you're going to get. First thing to note is that the peak of this portion of the cross-correlation function is going to be larger than the peak of this portion of the cross-correlation. That is because the cross-correlation is really a measure of the similarity between the signals. And since this triangle is identical or equivalent to this triangle, the signals are going to be more similar, so the peak is going to be higher. This triangle is less similar, although it has the same area. The shape is less similar than our x of t, so the value of the cross-correlation is going to be less. You should confirm this by doing out the integral, but it is going to be so. The other thing to notice is that the location of the peak corresponds to the location of these two non-zero portions of y of t. So this kind of highlights the main reasons why we would want to use the cross-correlation. First off, it tells us how similar a set of signals are, and it tells us the delay of one signal with respect to another. So these are two very important properties of the cross-correlation that are used all the time in biomedical signal processing and also in communication theory, electrical engineering. It's used a lot. So to summarize, RXY, the cross-correlation, this should be of tau instead of t, is a measure of similarity between the signals. The more similar the signals are, the higher the value, higher the peak of the cross-correlation is going to be. And the location of the peak of the cross-correlations can indicate the amount of temporal delay between a set of signals. So in one of our next lectures, we're going to be talking about some applications. And the first one we're going to be looking at is spike-triggered averaging. So how we can use cross-correlation to automatically average a motor unit action potential to get a really clear picture of the shape of it. And this can be important in diagnosing different neuromuscular diseases, for example. The other is we're going to go back to determine conduction velocity. So we're going to use the delay, how the cross-correlation gives us access to the temporal delay between signals, and we're going to use that to help us determine what the conduction velocity of propagating motor units are. So these are some real-world applications that I've used in the past. They're used quite often, actually. And just to leave you with a practice problem that I'll go over in the next online lecture, you should be able, this is a very simple problem, you should be able to do this very easily. So I would try it before you watch the next online lecture. But you should be able to show that xy of this should be tau, tau and not t. So work that one out, and we'll go over it in the next online lecture.